Hello guys, so today our topic is about sound waves, okay? And I guess it's the simplest part in the sound waves, or like the total part in waves, okay? So let's move into the sound waves part. So here we can find there's a figure in first slide, and a person is using his hand and his holder a hammer, right? And after he using the hammer to make like a crash on the block, and it has a sound, right? And now you are using two microphones to detect the sound. And you can find the sound first traveling to microphone A and then to microphone B, right? And maybe they have a time delay because the sound has a traveling speed, right? So now you can using like a control unit to find the time difference between the two waves. Okay, and here you can find on the screen, it reads 0.003, right? And that means the time delay for the sound from microphone A and then to microphone B. Okay, and also you can use your ruler to measure here the length between the two microphones. Okay, and maybe here you can find the length is 1 meter for two microphones, and the time delay is 0.003 seconds. And using this experiment, you can use the formula that velocity equals to distance over time taken, right? So here is velocity equals to distance over time taken. So here the distance is 1 meter. So here is 1 meter. And the time taken here is 0.003, right? So here divided by 0.003 seconds. And the value or answer here is 330 meter per second, okay? So this is for speed of sound, okay? And after you measuring this, you can just maybe try to determine that it may be in the normal distance, no, sorry, normal circumstance, the sound has a speed of 330, okay? In most tests, there are also another value called 340 meter per second, okay? They're quite similar, but they are in like in the different situations, they just equals to 330 or 340, okay? Okay, so let's move into the next part. And here you can find the second slide, we discuss about the speed of sound in different environment. And here we can see the figure, and a train is just having a sound, maybe it has beep beep, and then it gives up the waves. And you can find the person very far away from the train, maybe can hear just one sound. But to determine that, here are two materials, or we can just like consider there are two medium for the sound traveling. First, you can find there is a very close place near the ground, and this place is very cold because it's at night, right? At midnight, the ground is very cold. So the air closer to the ground also gets colder, okay? And maybe we knew that for the colder air and the particles move less frequently and the speed or average speed of the particles decreases, right? And that means they have a slower vibration or their traveling efficiency for sound just decreases, okay? And they have a slower sound waves. And maybe from you can find here the upper air has a because it's very far away from the ground, right? So the temperature for the air is very high, and we can say it's warmer air. Okay, so warmer air we knew that in the thermal physics part we know that like temperature increases, the average speed of the particles increases, right? So they can traveling or take away the sound more efficiency, right? So we can say that in warmer air their velocity for the sound speed increases, okay? Because there are two difference. So then you can find there are two paths for the sound to travel, right? One is very slower, but the total distance here is slower. And another is velocity is bigger, but the distance is bigger, okay? Like it's this way. So here we are discussing velocity and distance. So because of this, we can find we cannot distinguish two like echoes. That means they have the same time taken for two different paths. Okay. So here we can determine that velocity is bigger because the distance is bigger. And if you're using like the time taken equals to distance over velocity, they have the same value. Okay. There's warmer air divided by the warmer velocity equals to the like colder air distance over the colder air velocity. Okay, so here is for the speed of the sound. Okay, and after you having this formula, we can just try to measure other materials or other media and the sound traveling speed. Like here in the dry air at 0 degree, the traveling speed is 330 meter per second, and maybe 30 degree is 340, 50, or sorry. And in the pure water is 1,400 meter per second, and in the concrete, its velocity is 5,000. So you can find from air to liquid to gases, the speed increases, right? This is the first property for this. And second, we can say that when temperature increases, the velocity increases, okay? So if your question in P4 just want you to answer that why the speed of the sound traveling faster in solids and liquids and gases, maybe you can use in a perspective of particles, right? Because the sound waves need vibration to traveling, right? It's just like a transverse wave is vibrating direction just like perpendicular to its traveling direction, right? So here we can just draw a graph for the wave, like here. And this particle vibrates and then let second particle vibrate and third particle vibrate, fourth particle vibrate, fifth particle vibrate, right? And it can make all the particles on the wave vibrate, okay? And that's why some waves can like transfer energy, okay? So for this, we can say that because sound waves can traveling or it can takes energy. So right here, we can say that, oh, so temperature increase that makes like vibrating speed or like average speed for particles free motion increases, right? So it can have a higher efficiency, right? And also for this, like in the air, the particles are very far apart from each other. And then in liquid, maybe they're colder. And in maybe, sorry, here is solid, okay. I found there's a mistake, okay, here is solid. And for solid, we can say their density is the highest and they can traveling for a very high speed, right? So this is the difference between air, liquid, and solid. Okay. So right here, we can set the basic understanding for this, okay? Okay. So maybe next we are moving to echoes. Okay. So echoes we are very often seen heard in our daily life, right? So echo just means a sound just passes through and then hit on a wall or hit on a mirror and then reflects back, right? This is echo. Okay. So maybe echoes can use in the like ocean's sonar. Like if you're driving an ocean boat and here and maybe the bolt is for detecting, and you can use your sonar here. And sonar can use out the sound waves and to detect what is the shape of the sea ground, like this way. Okay, so please remind that for echoes, we have the two distance. Like first, the sound waves just moving downwards, and then it reflects. Okay, so here are two distance. So if you want to use in the formula for distance, velocity, and time taken, so here is distance to remember here times two. Okay, the distance means from the both bottom to the like the surface of the sea ground. Okay, the two distance equals to the velocity of the sound times the total time taken. Okay, so please remind here 2 times 2. Okay, so I guess echo time is also very easy for you to understand. And here there's some nature of the sound waves. And here you can find there are three instruments. The first is drum, and the second is guitar, and the third is vibrating probe, right? So we can say that the guitar, why it can have a sound, that is because we are using your finger to make the like the string vibrate, right? So this is why guitar can have the sound, right? So once you're using your left hand on this place and using your right hand on the middle of the guitar, right? You can find you're just using your finger to make it have sound, right? So this is how guitar have a sound. And also for here, you can find you're using like a sticker to hit the drum, right? And the drum can vibrate on its surface. If you put some very small and tiny like tissue on this, you can find the tissue just jumps up and jumps down, right? This is also because the surface of the drum will vibrate, okay? And for the tuning fork, if you are going to the lab, your teacher may give you an experiment like this. Everyone has a fork, everyone has a fork, and you're using just like using a small hammer to hit on the fork, okay? And then you can find the fork vibrating prong, and it has a very sharp sound, okay, for the tuning fork, okay. And there are also some natures for the sound waves. Like here, you can find sound waves are longitudinal waves, right? And also you can find sound waves need a material to traveling through. Okay, this is for sound waves property. So you can find some astronauts are in the space and they cannot contact with each other just by their mouths. They have to using like a microphone or like using an like detector and microphone system to traveling for the sound. Okay, so they can have a communication by this way. Okay, so here's the experiment. You can find there is maybe a jar, and here inside of the jar we have an electrical bell and a rubber band. And here the battery just connected to the bell and makes a bell to rings. Okay. And if you have a vacuum pump on the bottom of the jar, you can find once your the pump sucks more air in the jar, you can find the sound in the jar just become less and less. Okay. So we can say that here in the glass jar, the bell ring just depends on the air molecules, or it depends on the medium. Okay. So why is this? We can also using a perspective of particles, right? Because particles vibrate can travel in the sound, because sound just depends on vibration, right? So for this particle to vibrate and this particle to vibrate and this particle to vibrate, and finally it makes a jar particle vibrate, and then the sound can traveling outside of the jar, right? But if you're like the density of the air, or like the percentage of the air in the jar just decreases, you can say that the density for the air just decreases, right? So here we can say that so once it becomes a vacuum, the sound just dies down. Okay, so we have a conclusion for sound waves need a material to travel through. Okay. So there are some last last three lectures. I think it's very easy for you. So here sound waves can travel through solid, liquid, and gases, we have already discussed before. And also sound waves can be reflected and refracted, and also can be diffracted. Okay, there are three main properties for sound waves. Okay. Okay, so let's move into the next part. So over here, we are discussing about the ways of reducing sound. So I remember when I was a child, I always sneak her outside and to try to steal my phone, because at that time my mom restricted me to playing the phone. Okay, and at that time, if you knew, maybe I was very at a different age with you. So at that time, the phone brand is only have Nokia. Okay, and I played Nokia, and I remember here's a very small game on the tiny screen. Okay, like this way, a person who is, or like a soldier who is holding his gun to try to breaking through different of barriers. Okay, so this is kind of games is very fascinating for that time. Okay, and at that time, just sneak outside to steal the phone. So at that time, I just want to reduce my sound, not to let my parents to hear my the sound of stress. Okay, so here I just want to using some carpets or like some curtains just on my feet, right? Because you see my like socks or taking slippers, and because my house roof and the cylinder and roof, all the places are made by wood. Okay, so it's very easily to make the wood to have a crack sound. So it's very hard for me to get the phone from me. Okay, so you can find if you have the carpet on the floor, they're just making the sound, or they're dies down at the source, right? So first method is to reducing the sound from its source. Okay, so this is the first method, reducing the sound from its source. Okay. So next we have another way to reduce the sound. We can just block it on its way. So I remember when I was in Los Angeles, I just lived in the places very close to the Los Angeles International Airport. Okay, so at that time it's very noisy for me every day, because I had to heard that, oh, the airplane just flies here and flies back, and every night I had to close down all my windows, and I had to close maybe my another roommate for mine, he making some like papers, examining some towers, just putting in the like places of the two windows. Okay, and to stop the sound. Okay, stop the airplane sound. Okay, so we can also say that this method is just for reducing the sound on its path, right? So we can say the second method is reducing the sound on its path. So I remember here is a IGCSE P4 lesson, P4 test, and here is a question for you to ask that how we can reduce the sound. Then you can say that, oh, we can reduce it by sound by two ways. First is to reducing it on its path. Second way is to reducing it on its surface, on source. Okay. So here is the exercise. Please just try to solve the problem, please. Okay, I guess you have your answer, right? So here we choose A, right? And how we calculate this? Because speed of the light is very fast, right? 3 times 10 8 meter per second. So the time taken for the sound travel, for smoke traveling, maybe just nearly to zero, right? The time taken is near to zero. But for the sound, it has very slow speed, like it's 340 meter per second. So now we have to using the distance 100 meter to divide it by 340 meter per second. And we find that the time taken is 0.29 seconds, right? So the time difference or time delay for the sound is 0.29 seconds, okay? So now we're choosing A, okay? This is for this problem. Okay, so today we already discussed about sound waves. I guess it's very easy for you to understand. So please take the notes very carefully and just to doing some exercise after the lesson, okay? See you next time. Bye.